Because I'm glad you said that, because the reason I'm saying this is because I put the scores in, and then when I went on to grade, I found test two and there's nothing there. I put them in again. So that's been two assignments called test two. That must have come over from when I imported the spring class.
No due date test. This is the normal no due date test one. And then up here is this one. Test two, let's take quiz.
Is that the okay, now which one?
It's not the practice. I think I should input twice.
Well, that's exactly what happened though, is I
So I'll send you an email and maybe you'll just delete that one of those minutes completely. I'm not sure.
yeah, the one I'll is probably this one here. That was an
I would
online
take
one.
that one
Yeah.
away, yes. Test.
Okay, so let's talk about a reaction. A reaction's got two parts, reactants and products. Now, for a reaction to happen, the reactants need to be broken up. So bonds need to be broken. That requires energy. So all reactions require energy to start, just like when you're starting a fire. It just doesn't automatically happen. It needs some heat to get it going, and that's the energy. So once the energy is there, the bonds are broken in the reactants. And then if the products are more stable than the original reactants, they'll form into products. If they're not, it'll go back to the reactants. Uh, I'm going to have to restart this. Dadgummit. Oh, I know what the problem is. Got to plug all the wires in. Okay, so if we were going to look at a diagram, this is going to be potential energy. And we know that the lower the potential energy, the more stable it is. So if we have reactants here, and if the reaction is going to go spontaneously, the products need to be at a lower potential energy. Now, the route to go from reactants to products, however, goes through a much higher potential energy. And that's because the bonds are being broken, which is not stable, energy is being applied, and all this stuff. So it gets to be a very unstable state. That state is called the activated complex. And that's where everything is jumbled together, where all the atoms are free from the original structure. And then two things happen. That activated complex bundle wants to go here or here, because those are the two more stable states than the activated complex. And depending on how stable this is, more will go over here, but there's always some that go back to the reactants. And it's important to realize that. And it's just back and forth. It happens all the time. And there's a state that you get into called the equilibrium state, where the number of reactants equals the number of products. That's called equilibrium. And there's a whole chapter in 1A on equilibrium. And it's quite a big chapter too. Okay, so the main thing though is we have energy being required, and that's this energy here. That's called the activation energy. Basically, that's the spark. Now, interestingly, if the reaction produces heat, like a fire, it produces its own activation energy. So you don't need to keep putting sparks there. Now, there's another situation where the products aren't as stable as the reactants. And these reactions do go, because there's another component in whether a reaction will go or not, besides potential energy. There's another one called entropy. So potential energy, which is fancy name, it's called enthalpy, and entropy together make a reaction happen. So if we're just looking at potential energy and you see that there, you'd say the reaction wouldn't go because the products are more less stable than the reactants. But there's another, the entropy could be such that it would force it to go. That's why when you have a cold pack and you break it, it gets cold. That's called an endothermic reaction, because energy is required for the reaction to go. So this reaction here, because the products have a lower potential energy than the reactants, this is called an exothermic reaction. That means if you're holding it in your hand, it'll get hot because it's sending energy out of the reaction. And if you're holding it, that means your hand's going to receive it. Think of hot. This reaction, you still got an activated complex here, just like the other one. This is called an endothermic. Like the coal pack, because it requires lots of energy to work. So that's a reaction, reactants, products. Every reaction, the reactants will break apart, form an activated complex, and then fall down either way to either product side or reactant side. So let's look at, oh, and by the way, Tuesday's lab, I mentioned the reaction that goes on in a Bunsen burner. For the Thursday folks, we're gonna be using a Bunsen burner tonight. And you're gonna be responsible for the reaction inside the Bunsen burner, which is methane plus oxygen gives water plus carbon dioxide. And there's gonna be a pop quiz Thursday, a week from today, on exactly that. You'll see it tonight. Okay, so let's take a reaction. Let's take something like
happens between the reactant and the fission state, or is that like, is there an example of what activation?
It's the energy required to get the reaction up to the activated complex.
So there's like, is there an actual,
A what?
like, what's an example of that?
You have a little wood fire. Does a wood fire start itself? No. You need matches, right? And the matches supply the activation energy to get it going. And then you don't need any more matches because the energy given off will activate itself. Oh, let's see, sodium hydroxide. Okay, calcium chloride plus sodium hydroxide or lye gives us calcium hydroxide plus sodium chloride. Okay, so the question, remember the 4 steps of stoichiometry. The first step is balance the equation. If there's a reaction that's going on, you got to write the equation, or if it's given to you, make sure it's balanced. Okay, because if you don't do that, the rest of the steps, you're going to be in error. So it's extremely important to be able to balance equations. Okay, so how do we know if it's balanced or not? The first thing we're going to do is we're going to take an inventory. Okay, we've got calcium, we've got chlorides, sodiums, oxygens, and hydrogens. All right, so how many calciums are on the left? 1. How many calciums are on the right? 1. That's very good balancing. We start with 1 calcium, we end with 1 calcium. Okay, what about chlorides? How many do we have on the left? 2. How many on the right? 1. So right away we have an unbalanced equation. Okay, sodium's on the left. On the right. How many oxygens on the left? 1 on the right, 2 hydrogens, 1 and 2. Okay, so clearly this is the inventory. I call this, you have to take an inventory of the reactant atoms, product atoms. And they've got to be the same numbers. Otherwise, we're going to have a big nuclear explosion. No está bien. Not good. Okay, so we've got to change some of these numbers. The only numbers we can change are the numbers out front. Those are called coefficients. Right now, there's none or 1. If there's none there, it's assumed to be 1. You cannot change the subscripts. If you change the subscripts, you'll change the molecule. Okay. So any suggestions on what to do? Does everyone see, by the way, this is not balanced? Okay, all right. We've got 4 numbers we can change. Yeah. Okay. As soon as you put a number down, new inventory. Okay, so that affected this number of sodiums here and the number of chlorides. So now we fixed the chlorides. We've still got some issues with the oxygen and hydrogens. What else can we do? Yeah. Okay, that makes this 2, that 2, and that 2. So how are we doing? It's now balanced. So if I asked you to show me that the equation is balanced, this is what you do. You do an inventory of the reactant side and the product side. And again, I want to reiterate, very important, the only numbers you can change are the coefficients out in front. And you can put a 1 here if you want. That's perfectly fine. So this is the deal. Guess. His first guess was putting a 2 in front of the sodium chloride. The check part is doing the inventory. And there's a lot of places to start. We could have started over here on the left side. We didn't have to start on the right side. It's totally random, unfortunately. It's not analytical at all. Now, the other method I was telling you about is very analytical. But this process, which most people use, 99% of the people use this method. It was funny, I taught a 1A class for engineers about 6 years ago up in Washington. And so everyone in the class had differential equations, calculus, linear algebra and stuff. And the funny thing, in their linear algebra class, they used balancing equations as an example on solving a system of equations. They all knew how to do it. So that's all they ever did. They didn't do guess and check. They go, oh, that's really inefficient. We learned another way to do it. So, okay, let's do some more. Now I have lots of practice for you also. If you go to files, I've got lots of worksheets on it. Lots of worksheets. Okay, are there any questions about this guy? Okay, so let's burn propane. Propane is a C3H8. We burn it in oxygen. It's called combustion, just like our Bunsen burner, only this time it's propane. And all combustion reactions start by oxidizing each element of the fuel. That means carbon's oxidized carbon dioxide, hydrogen's oxide, that's called water. Okay, so let's take an initial inventory. So we have CHO. Okay, so we've got 3 carbons on the left, 1 carbon on the right. So right away, unbalanced. Okay, so you can see that's a very unbalanced equation. So once I take a crack at where we start. Anyone? Don't all speak at once now. I'll have trouble hearing you. How about if we started the carbons? Okay, that makes, now we have to redo the inventory now. That means that's 3. And it changes also the number of oxygens. Okay, so that's 6 oxygens plus 1 is 7. Now we fixed the carbon, but nothing else is balanced. So what are we going to do now? How about the hydrogens? What are we going to put in front of the water on the right? 4. Now that's changed the oxygens once again. So we got 6 plus 4 is 10 now. So everything is fixed except for the oxygens. What can we do to fix the oxygens on the left? 5. So it's balanced now. Guess and check. And make sure, because frequently when you change the coefficient, you change more than one thing. Are you feeling better? Be with her. She knows what she's doing. Weren't you together last time? Yes, she knows what she's doing. Okay, I want to do another one again. I'd like to kind of continue doing these for a while, give you lots of examples. Let's do some more combustion. Let's take butane lighter. Let's do the chemistry of that butane lighter. A butane is a 4-carbon hydrocarbon. 10 hydrogens. Okay, I'm going to burn that in oxygen. And it's going to be carbon oxidized plus hydrogen oxidized. Let's take an inventory. We've got CHO. So obviously, 4 carbons and 1 carbon, right away we know this isn't balanced. 10 hydrogens, 2 hydrogens, 2 oxygens, 3 oxygens. Okay, so it's horribly unbalanced. Okay, now it changes the oxygens though. We've got 8 and 1 is 9. So how can we fix the hydrogens? So we're going to have 8 and 5 is 13 oxygens. Okay, so everything's balanced except the oxygens. What can we put in front of the O2 on the left to make it 13? Fractions are okay. So what fractions can we multiply 2 by to get 13?
26.
26.
Oh, I'm sorry.
What do we multiply? Right. Yes, 2 times 13 is 26. You're correct there. What can we multiply 2 by to get 13? 2 times what is 13? 6.5. Or 6.5 or 13 halves. Okay, so it's balanced. Now there's a problem that you can't have fractions as a coefficient. So what can we do to clear the fraction here? Multiply by what? No, it's actually correct. How do you clear fractions? By what? By 2, exactly. So we multiply the whole thing. Think of this as an equation. If we multiply 2 by the 13 halves, we'll end up with 13. So, but we have to, what we do to it, we have to do to everything. So we're going to go okay, now it's balanced with no fractions. So it's fine to balance it with fractions first, but you have to clear the fractions if you have fractions. And you'll never, usually it's by 2, sometimes it's 3, never anything else, either 2 or 3. And 3 is rare. So most of the time it's 2. Okay, so a couple statements about balancing equations. Number 1. Balanced equation is a molar relationship. And here we go again with the moles. It's a molar relationship. And it's a molecular relationship. So what they mean by that is 2 moles of butane will react with 13 moles of oxygen gas, gives us 8 moles of carbon dioxide and 10 moles of water. Or 2 molecules of butane plus 13 molecules of oxygen will yield 8 molecules of carbon dioxide, 10 molecules of water. Okay, so this is it's not a mass relationship. It's only molecular and molar. So in other words, it's not 2 grams and 13 grams, all that stuff. You got to convert everything. If you have any grams or anything like that, it's got to be converted over to moles. And that's what we're going to get into a week from today. I'm going to say, yeah, you have 15 grams of butane. How much carbon dioxide do you make? So there's a distinct way to do that. I'm going to show you. Okay, so it's important. This is what a balanced. So all balance. That's why it's important to balance the equation so you can see the molar relationships. Okay. Let's practice some more here. Let's do Jack. Can I borrow that worksheet of yours? One's fine. Now this worksheet I'm getting the examples from is on files. It's called Balancing Equation Practice 1 and 2. And I think there's 3. Are there 3 of them or just 2? Yeah. And the extra credit one problem is there, by the way, also. So if you want to get a head start on it. Okay, so let's just do some of these. I want you to try these on your own first. Okay, so go ahead and balance that. That's a nice t-shirt. I told the department chair that one of your hobbies is glass blowing, and you had a glass lathe. I'm like, no,
Really? That's awesome.
it was pretty cool.
I'm making some whiskey tumblers for a buddy of mine right now.
Oh,
They're doing like a sort of a fluted glass with a kind of pedestal like that.
Hmm.
A little narrower. And then it's got a color bit. And the base is colored too.
at my trash can, people may want to give away stuff. They'll put it by the trash can. There's a hand-blown glass bowl with a tube of different colored glass going around. A big bowl and a nice plate and everything. I grabbed it.
That's sweet.
Yeah, yeah. my daughter was really impressed when she, look what I found. Claudio,
Since there's nothing on the bottom.
you got, yeah, two there and one there, just, actually, yeah. Two oxygens plus three oxygens, six oxygens, right? Yeah, sometimes the, stuff is in multiple molecules.
No, I just forgot all this.
And that's what's hard about the extra credit. It's got stuff that's in all of them.
Oh,
Yeah, it's a real pain. Yeah, that looks fine. Yeah. Hmm? Well, I mean, unfortunately, it's a guessing check though. So yeah, and sometimes you can start in any place and do it. But sometimes it's best to start with the most complex molecule first. And then in that case, it's they're all kind of the same, but sometimes you'll have, like the example I gave before with the butane, you kind of start with that one, like doing the carbons first on that one, because it affects so much other stuff, because it's a bigger molecule. If it's a simple molecule, it doesn't affect anything else, but that's the only strategy I can suggest, which is not much.
Especially for the extra.
Oh, the extra. It is a pain. I'm serious. It's a pain. Not very big. It's just hard. Yeah, if you go to files. Know what's that, Claudio? First, take an inventory. How much nitrogen, hydrogen, oxygen you got on each side?
One.
Hmm?
For how many types?
Yeah, how many nitrogen you got?
3.
No, one. You have 3 hydrogens.
I have 1 nitrogen.
Mhm.
1 nitrogen.
Mhm.
I'll have 1.
So you go like this. You have N's, H's, and O's. You have 1 of each. 3 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. So the hydrogens right now. Yeah. Hmm? Right. So you got to do something with the coefficients to make them balance. So fiddle with the numbers, inventory. Fiddle with the number, inventory, just like I did the inventory here. You keep fussing with it till the numbers are the same number.
How will I balance? That's what
Well, I mean, you've got 3 hydrogens here, 2 here. So what if you put a 3 here to make it 6, and a 2 there to make it 6, and the hydrogens do balance. But the other things wouldn't balance. So you have to keep fussing with the numbers. And I can't say your husband's a chemical engineer.
No, my friend is, but she started dating.
Okay.
She's like, busy right now. I haven't been able to.
Oh, okay. I was gonna say really handy for husband. He's an engineer though, right?
Yeah, he does like structural and like
Yeah.
railroad.
Yeah. Well, I hate to say it, but you just have to fuss with these numbers.
Okay. I just didn't watch it. So, but I wasn't paying attention.
There are tons of internet videos on this.
And that's what I've been doing lately. But my friend started dating this. This is her last year. So sometimes she tutored me a little bit, but then when she started, she's like,
Yeah. Right. Right. Okay, we'll start. Change a number and then take a new inventory. And you keep changing the numbers till the numbers work out. Yeah. Oh, yeah, good. You get it?
I think this way is a lot worse though, and I wouldn't recommend it. It'd be like,
Fractions are fine, you just have to clear them in the end.
Are you gonna show us how to do like a matrix?
No, but if you go on to Canvas, I have a document that explains how to do it. There's no one in here. And if you can't find it, email. I think it's there. Are you on Canvas right now?
Oh, that can be. Is it files? Is it documents?
Files.
Files.
And then, let's see, what, these are all
The
worksheets.
equation
Yeah.
or the examples.
Is the extra credit one there? Let's go to miscellaneous. Right there.
Oh,
What kind of calculator you have?
I have a graphic calculator at home.
Yeah, this will work on an 83, 84, 89.
One of the basic ones.
Yeah. As long as you can, as long as you can do matrix on it.
We have this on like three top before. That's why I remember.
So what you use something called reduced row echelon. RREFF. But it doesn't tell you what to do there. On the test?
Yeah.
Yeah. Yeah. Okay. All right, so let's go through this. A lot of you are starting to get it. But it just takes, you're gonna have an aha moment when you do a bunch of these. If you go to files, the unit, I think it's unit 5 that says stoichiometry. That's what unit we're in now. There's a whole bunch of worksheets there, a whole bunch. And if you want to learn how to do it via the matrix method, go to miscellaneous files. And the top one is how to do it via a matrix. But you have to have a calculator that does matrices. That's like 83, 84, 89. There's others anyway. But it's got to be able to do matrices. Okay, so we have 1 and 1, 3, 2, 2, 2. Okay, so we have some issues with the hydrogens. So you want to try to fix them first? Okay, we got 6 and 6. But that also changed other things. It changed the number of nitrogens to 2. And the oxygens are 4 and 2. Hasn't changed. Okay, so we still have problems. Nitrogens are off. So let's put a 2 there. Fix those nitrogens. Okay, so that also changed the number of oxygens. So we have 3 and 2 is 5. Okay, we have the oxygens now. How can we fix the oxygens? Well, we got 5 on the right, 2 on the left. What can we do? Five. Now we have 5. Well, we got to clear the fraction now. So we're going to clear the fraction by multiplying everything by 2. So if we do another inventory, we're going to end up with 4 and 4, 12, 12, 10, 10. Now I want to show you something. Is everyone okay with that? Okay. Let's say so instead of a 4, 5, 4, 6, I had 8, 10, 8, 12. You can have multiples all over the place of the coefficients, as long as it's broadly applied to all the coefficients. So the top equation with 8, 10, 8, 12 is still balanced. Nothing wrong with that. Because on Thursday, week from today, we're going to be using ratios of the coefficients. It's always going to be a ratio. And 1/2 is the same as 2/4, same as 4/8. So if your equation is got a multiplier of 2 or 3 in it, it doesn't matter because we're going to be taking the ratios of the coefficients. So they're both balanced. Some books will say, is there a common multiplier, you know, where you can divide it out and all this stuff? It doesn't matter. If it's balanced, it's balanced. Okay, so let's do one more. Are there any questions about this guy? Go ahead and try that one on your own. Why don't you work on this one on your own? This is a lot harder. Work on this one. I want you to get the idea down.
Because basically, I did divided times 2, that's counting together. Which gives me 6.
Why don't you instead of writing 2 times 3, right? 6 there.
Mhm. So this-
Okay. So that's good.
But then what do I have to do next? I'm confused. How do I balance the nitrogen?
Well, you got 2 there and 1 there. What can you put in front of the NO to make it 2?
Two.
A 2.
Well, because I added. So if I add the should to this one.
No, yeah, you can only add it in the
to
front.
left- to the
Front only.
Okay, so then now that's 2. So then that's a 2 and that's a 2.
You gotta put a 2 there though. As soon as you do that, you have two O's here and one O there. That makes that 3.
Plus 3. And that makes it, that's 2. So then I have to do times it again. Times 3, times 3. Got it.
No. You have to change the number here first. Then you take the inventory.
I don't get it.
Yeah, and leave room in front because you're going to be putting numbers there. And then a pencil is handy.
I know I don't have one today. I usually have. So we have 1 nitrogen, 1 nitrogen.
Mhm.
3 hydrogens, 2 hydrogens.
Mhm.
Oxygen, and 2. And 2.
Mhm. Okay, but the issue now is to start with are the H's.
And that's when I did times 3 times 2 times 2.
But before you do that, look at, okay, so here's 3 hydrogens and 2 hydrogens, right? What are you going to put out here to make that
A
6?
2.
A 2. So put the 2 there. Put the 3 over here. Okay, so now it's 6 and 6. Okay. But you now have 2 nitrogens, 1 nitrogen. You see, when you put the 2 there, it affects both the nitrogen and the hydrogen.
So then this equals 2. So now I have to times 2.
And the 2 there, though. And see that now change the oxygens. So we have 2 oxygens, 1 oxygen. So that makes that 3 over here.
So if I have 2 here and then 2 here, wouldn't that be 4?
No, you have 1 here. You have 2 hydrogens.
Oh, so that would be 3.
3 and 2 is what?
3 to
The
5.
oxygen.
Times.
Okay, so you have issues now. Everything's balanced except for the oxygens, right? God, can't blame the smoke. So what can you multiply 2 by to get 5?
Can't multiply anything to get 5. So yes, you can't multiply anything to get 5.
There you go. 2.5 times 2 is what?
Oh, yeah. 2.5.
Or 5 over 2 for fractions, 5 halves. That's what's going to go in here. Not yet. No, because 5 times 2 is 10. You gotta put 2.5.
Oh, yeah, that's true.
Okay. So 2.5 times 2 is 5. Put 5 over here, so it's balanced now. The problem is the 2.5. If we multiply everything by 2, 2, 2, and 2, fraction becomes, this becomes 4, 5, 4, 6.
So then it would be.
So then redo all the numbers.
Could be 4.
Yep.
That'd be 6. Yes. I
No.
have to multiply this.
No, just
Just the beginning.
because the coefficient is the one you're going to be multiplying. And then 2 times 2.5 is 5, right?
Like that.
Mhm.
5 and
Yep,
2.
yep.
Right, so keep it in that.
Mhm. And then 2 times 2 2 times 3. Mhm. Yep.
Oh, okay.
So fractions are fine, but you just got to get rid of them at the end.
I had to look for the fraction busting.
Yeah. How are we doing?
Oh, we were just looking at, I was showing you like this trick and, with the electronic.
Problem with this trick, it works fine to get them memorize it though. The way I showed you how to do, it, you don't have to memorize it.
It takes a while. So if you can memorize that triangle,
That's right. I agree with you. But it's just one other thing you got to memorize. I don't like to have students memorize stuff when you do it another way. We,
but
oh, it's fine. Does it make sense?
This is, pretty straightforward.
Hmm?
Balancing equation is pretty straightforward.
Well, it isn't, it isn't. What do you see the extra credit?
Okay.
Then we'll revisit that.
Yeah. Okay.
Your work?
Yeah, it was more apparent for me than the last one. I just saw it faster, but.
Good. We'll look that up. Okay, I'm going to do one more. And I'm going to show you sort of a trick. The next one. Oh, I gotta grab it for you. Okay, so that would be that guy. Now, what I'm going to do on the next one, this is the last one, and this will be the end of class today. This is the hardest one on the worksheet. Okay, this is definitely a challenging one. And there are 2 ways to work this. And in a little while, I'm going to show you my opinion, the simpler way to do it. Don't do this one. It'll, I want you to just focus on some things.
4.
Yeah.
Okay.
Let me redo that. It was very handy you had this printed off. Because to come up with these is out of nowhere is a pain. Just making sense.
These multiply.
It's 12.
Be 12.
Yeah, parentheses means whatever's in the parentheses 3 times. Huh?
For this one's like 1, right?
Yeah.
Yeah, so this is 1 as well, right? And this
But
one,
it's 1 for the, yeah,
so one of this,
actually it's 3 of these. See the 3 on the outside down here?
oh, yeah, so it will be 3 of this, right? And then for this one, the 8's with not parentheses, it comes like 1.
Yes.
Okay, just making sure.
And this is the way, the approach you're taking now is the approach I'm going to show everyone in a minute. So that's a really good approach. And I have to show you why or when you can apply it. Because you can't
Okay.
apply it all the time. You have to make sure they're there's one on each side of the,
They're actually like the same, like.
Yeah.
Right?
and PO4s, NO3s, NO3s.
Hmm.
Poquito más duro.
I know.
This is a fun one. This is a story of your life, huh? Doodle time, Ferguson's boring. Isn't this fun?
Um,
I know. She's going like,
So awesome, if I could just separate that.
keep that thought.
Maybe, maybe just take that. Move it, and then
Well, you can think of it that way. You can't really separate them, but you can think of it that way.
like, the coefficient has to be here, it can't be here.
No, coefficient has to be over here.
Over here.
Yeah.
okay, that's. There's no coefficient.
Right.
Okay. Ah,
Okay. Let me talk about this problem. This is a pretty involved problem, as you all can attest to. One of the problems with this problem is that you've got oxygen in everything. So when you change one thing, it affects a whole bunch of other things. That's a big red flag going like, ah. So I'm going to look at this problem. Instead of taking the nitrogen, hydrogen, phosphorus, oxygen, and lead individually, I'm going to be looking at this problem from a little higher level. And that level is looking at ions that are on both sides of the equation. Notice we have NH4 here, NH4 there. So instead of taking that as N and H's, we're going to take it as a whole group. PO4, PO4, again, phosphate, take it as a whole group. Nitrate, nitrate. So instead of taking individual elements, I'm going to take them as groups. So how many NH4s do I have on the left? I have 3. How many on the right? 1. Okay. How many phosphates on the left? 1. On the right? 4. Leads? 1, 3. And what about NO3s? 4 and 1. So it's not balanced. Now, you can do the same thing with the N by itself, H is by itself, but it gets a lot more involved because we've got oxygens all over the place. So we're going to take these as groups. You can just put down X, Y, and Z if you want. How many X's do I have? How many Y's do I have? How many Z's do I have? Now, to use this method, you've got to have the ions on both sides of the equation. No exceptions. It's got to be on both sides of the equation. So nitrate, nitrate, phosphate, phosphate, ammonium, ammonium. Okay, so let's start balancing this. Let's fix the NH4 group. We need 3 here. And that boosts, that kicks the nitrates up to 3. Phosphates, we have a problem with. We need 4 over here. Okay, that makes that 12 ammonias, 4 phosphates. We need 3 leads. And that gives us 12 nitrates. So if I put a 12 here instead of the 3, That'll give me 12 nitrates and 12 ammonias. All done. Huh?
That's very simple compared to doing it element by element.
So look for this in equations. Do I have a common group on both sides? She did it all on her own. I walked over there and she did it a slightly different way, but the same concept. She grouped them with a square around each one of them, which is not too bad of an idea. She went like this. She went. She grouped them like that. So, and that's probably, except for the extra credit, that's probably the hardest one you're going to get in here. This one we just did. So if you can do that, either the way we did it originally, taking everything apart, or using this method of grouping. Either ways works fine. Okay. My cough is starting to get worse again. It's like, oh. Okay, so that's it for tonight. Okay, so I wanted to cover balancing equations, and we covered quite a bit of that.